Hello and welcome to the launch show for Anton Paar's brand new thermal analyzer. I'm Anthony Mills and I'm delighted to be joined here today by Anton Paar's product manager for thermal analysis, Jiří Kyslinger. Jiří, let's get right into it. This is an exciting step into a new field. Why the move?
Anton Paar has long been the benchmark in fields of density, concentration, CO2 measurements, especially in industries like the beverages. But our portfolio already spans material characterization methods like rheometry, particle analysis, or X-ray diffraction. So adding thermal analysis was only a natural evolution in order to strengthen and complement our offerings.
Well, now let's get right to what our viewers are all waiting for, and that is, of course, the instrument. Jiří, tell us what exactly this new instrument is.
It is called Julia DSC. It's Anton Paar's new high-performance thermal analyzer.
And DSC stands for?
Differential Scanning Calorimetry. Calorimetry because it detects properties that are connected with exchange of heat. Scanning as the sample is scanned over time or temperature. And differential because it is actually the heat flow difference between a sample and a reference that is measured. And as for Julia, it is named after the unit of energy, the joule. And this device is all about energy, so efficiently used.
It's a great name. Let's have a look at the intro video.
Meet Julia Jules, the triathlete. She's all about speed. When she's running, when she's swimming, when she's riding a bicycle. She never cuts corners, because speed means nothing without precision, especially when it comes to thermal analysis. Introducing Anton Paar's Julia DSC. Julia takes no training. She's up and running right away. She guides you through every step. No steep learning curves. Julia takes care of quality control with the touch of a button. Julia gets down to sub-zero fast. She's compact. She doesn't need a chiller. Julia changes cooling modules in no time. Julia prepares methods in just a few clicks and streamlines your workflow with step-wise guidance. Thanks to Julia's auto sampler, you don't have to handle repetitive tasks. Julia Jules, Julia Suite, and Julia DSC, where speed meets precision.
Speed meets precision. Tell us more.
That is the core of Julia DSC. Speed meets precision. We've built this instrument in order to help users learn to use it fast, cool it down fast, and ultimately get the results fast.
It all sounds really promising. Tell us what makes the instrument so easy to learn how to use.
We talk about Julia Suite. It's the control and analysis software. It's been designed with real user experience in mind. No formal training required, and you can start using it within minutes. Mainly thanks to its intuitive design with step-by-step workflows, guided calibration wizards for total confidence, or a dedicated quality control mode with preset pass, warning, or fail criteria and performance tracking. So whether you're a newcomer or a DSC Pro, Julia Suite removes the learning curve.
Now, cooling sounds standard for DSCs. What's different here?
We have completely rethought DSC cooling. Julia DSC's air cooling module uses advanced patented Peltier technology that can bring the instrument down to minus 35 degrees Celsius. And now comes the plot twist. All without attaching an external cooling device. With this, you get unmatched cooling rates down to sub-zero temperatures with the built-in module, fast cooling in between measurements to speed up and improve the productivity, and it's efficient, fast, and reliable way of cooling.
And why did you choose Peltier cooling?
As I said before, it's clean, it's fast, it's efficient and effective. And it's also already proven by our other instruments like rheometers or viscometers. This way of cooling is perfect for most DSC application, and it saves labs time and hassle.
But there are other options too, right?
Yes, naturally. We also offer refrigerated cooling module. With external chiller attached, it can bring the instrument down to minus 90 degrees Celsius, or nitrogen cooling module with liquid nitrogen as the cooling option for cryogenic applications down to minus 170 degrees Celsius. What's best is that these three cooling modules can be swapped within one instrument freely. And I would suggest to ask my colleague Andrea to actually show us how fast and simple it is to exchange these cooling modules.
The cooling module can be exchanged even when the autosampler is still mounted on the instrument. The autosampler is simply moved into the so-called maintenance position. This makes all 4 screws holding it in place fully accessible. These screws can then be loosened using a conventional screwdriver, which is included with the provided accessories. Alternatively, if available, a power tool can be used, making the process both easier and noticeably faster. Once the 4 screws are removed, the cooling module is carefully lifted upwards, taken out of the instrument, and placed aside in a safe location. Installing the new cooling module follows the same steps as we have now seen, just in reverse order. It is positioned into the DSC, and the same 4 screws are tightened securely. No extra force is needed, just hand tightening is sufficient. As a final step, the DSC automatically detects the newly installed cooling module. It is ready to be used immediately, requiring no additional setup.
Thanks, Andrea. It really is remarkably quick, remarkably efficient. Yuri, what is the secret? How does Julia DSC speed up those workflows?
From setup to data analysis, everything is designed for speed. You get a method builder with graphical representation of the temperature program and the gas program and pre-filled suggestions. The navigation is streamlined for rapid graph customization, guided calibration checks with performance history tracking. You can start measurements directly from the touchscreen interface. And that status light, it keeps the user informed instantly, ready, measuring, in need of an attention. So there's no guesswork.
And how's the calibration of the DSC handled? I know that for some instruments it can be quite tedious.
Not with Julia DSC. There are built-in automated calibration wizards, whether it's temperature and enthalpy calibration, sinusoidal DSC or SDSC, even autosample calibration. Everything is designed to be guided, reliable, and fast, of course.
SDSC, that's new to me. I'm sure it's new to our viewers too. Yuri, tell us what it is.
Sinusoidal DSC introduces a modulated temperature profile into the measurement. And the result is the separation of the reversing and non-reversing heat flows. This is extremely useful when processes overlap. As an example, a reversing glass transition might overlap with non-reversing enthalpy relaxation. And as you might expect, the Julia suite will guide you through the setup of such a measurement so that you don't have to guess the optimum setting.
And what about automation?
Julia DSC Autosampler. It can help boost productivity of any laboratory with 70 sample positions spread across dual trays, 8 reference slots for reference crucibles that can be exchanged automatically depending on the method, Smart crucible handling, even for custom crucibles, and a waste container to get rid of used crucibles to free up space and maximize the sample capacity.
How about sustainability features?
Julia DSC has been designed for efficient, future-ready labs. The modular design extends the usability and thus the lifetime. Configurable eco mode helps cut down electricity and gas consumption. And the two features that I already mentioned. The touchscreen 7-inch interface for fast operation, and that status light that can reduce downtime. All of that with Anton Paar's commitment to innovation with purpose.
Where is DSC used?
Literally everywhere. You can find it in basic QC labs to advanced R&D. You can find it in industries, mainly polymers, but also pharmaceuticals, chemicals, including batteries and energy storage, food science, construction materials, the list would just go on.
And what does the output of a DSC measurement actually look like?
It is a heat flow curve, sometimes called a DSC thermogram. On this curve, we see peaks and steps, and they show us the transitions like melting, crystallization, glass transition, and reactions like curing or decomposition. And with proper analysis tools, you also get precise numbers too, like the transition temperatures or specific heat capacities. I think we can ask Andrea again, this time to show us how to prepare a sample, create a method, we'll run an experiment, and then we'll get the heat flow curve and we can talk about it more.
The provided accessory box includes all the tools that are needed for sample handling and preparation, whether the sample is a solid piece of a polymer, just like in our case, a powder, or a liquid. The sample container, called a crucible, is placed into a die. A die is the detachable lower part of the crucible sealing press. A small amount of sample, usually a few milligrams, is placed into the crucible, covered with a lid, and closed using the crucible sealing press. The prepared sample can then be placed into the sample tray and brought to the instrument. In order to start a measurement, there are only a few steps to go through. Give the sample a name, fill in the sample mass, and let the auto-sampler know the position in the tray. Creating the measurement method is facilitated by the graphical representation. In this case, we select a dynamic segment with a linear heating rate of 20 degrees centigrade per minute from 30 to 300 degrees centigrade, followed by a 1-minute isotherm. In the bottom right part of the measurement setup, the gas condition can be seen and set. By pressing Start, the auto-sampler automatically selects the correct reference crucible from the reference tray and inserts it onto the sensor reference position in the furnace. The prepared sample crucible is then placed onto the sample sensor position. The furnace closes and the experiment is started.
Thank you, Andrea. So, this is the output of a DSC measurement, a heat flow curve. This example is a material called PET, used in the production of plastic bottles. And if we look at the curve from left to right, at about 80 degrees Celsius, you see a step in the curve which denotes the glass transition. If we move along the curve to higher temperatures, starting at about 150 degrees, we see an upward-facing exothermic peak, that is a cold crystallization. And at temperatures above 200 degrees, we see a downward-facing endothermic peak, and that is melting.
That's really impressive. Thank you, Yuri, for this deep dive into Anton Paar's brand new thermal analyzer, Julia DSC.
Thank you, and welcome to the future of fast and precise thermal analysis.